Today we're going to be talking about how to find the electric field of a uniformly charged sphere, of a solid sphere, of course, of charge Q. So the first method we're going to use is brute force. We are going to attack this sphere with our bare hands. And so in order to do that, I'm going to recall the electric field equation E is equal to 1 over 4 pi epsilon naught Q over R squared R hat, okay? Where basically if I have a charge Q and a point charge, in particular point charge Q, and I look at a position, let's say R out in space, a vector, let's say cursive R, and this is consistent with the notation used in Griffiths, then yeah, if I have a test charge, maybe capital Q here, and I look at the electric field, which is the force exerted on that test charge divided by its charge, I can recognize that experimentally this is the equation for the electric field. And so generalizing this to if I have a continuous charge distribution instead of just a point charge, let's say I have a sphere of a certain charge density, then the equation is slightly different. So for a continuous charge density, I know that my electric field is given by 1 over 4 pi epsilon naught. And now instead of a q, I'm going to have a dq, and I'm going to prime it. So all primed coordinates are going to be with respect to the source charge, and all unprimed coordinates are with respect to the test charge. Okay, and this is again consistent with the notation used in Griffiths. Now I'm going to, so instead of instead of the point charge q, I'm going to have dq prime, and then I'm still going to have this r squared r hat, but now I'm going to be integrating over the entire, in this case, sphere, and over the entire region of charge. Okay, so in particular, we're integrating over the primed coordinates. Now r squared, this cursive r, is in fact the vector that points, if I start at, let's say, source charge dq prime, and I take a point in space, I'm looking at the vector that goes from that source charge to test charge, or the point in space where I want to know the electric field. And so that's my r, and in particular, cursive r is equal to the vector location of the test charge, or where we want to know the value of the electric field, which is r. So in this case, this is r here, and then I'm going to subtract the vector location of the source charge, which is r prime. Okay, so r prime is the vector that I take from the origin to get to dq prime. And so due to the symmetry of the sphere, we really only need to be calculating the electric field at a single point or along a single axis away from the sphere, and we know that it's going to be radially symmetric about the sphere. So we might as well choose the point. So we're going to choose the point r is equal to 0, 0, z, where let's say the sphere has radius, maybe capital R, and z is going to be greater than capital R. Okay. All right, so in doing this, all that's left to do is just set up this integration carefully. So first thing I'm going to do is I'm going to get rid of the r hat. So the hat denotes a unit vector that just gives us the direction of the electric field. But since I'm integrating, notice that this direction, little r hat, is changing, because as I integrate along the sphere, obviously, I'm going to have different source charges contributing infinitesimal amounts, little r prime, in different directions. And so I'm actually integrating over this r hat vector as well. And so to simplify this expression, I'm gonna write r hat as r divided by its magnitude, which I'm going to just call cursive r. And so I'm going to get dq prime, which is the charge density dv prime. Okay, so that's the definition of dq prime, divided by r cubed. And now I just have the actual vector cursive r. I've gotten rid of the hat there. Okay, and this should be a cube. Okay, perfect. So I kind of did two steps at once there. This dq prime is rho dv, which is like standard theory for if you look at, you know, the charge of a differential piece of a volume, it's just the charge density. The definition of charge density is literally, you know, dq over dv prime. So it's kind of the definition of what charge density means, where rho is the charge density. Okay. And finally, since we know that this is a uniformly charged sphere, we know that that's basically telling us that rho, the charge density, is uniform, and it's precisely going to be equal to the, excuse me, it's precisely going to be equal to the charge of the sphere divided by the volume of the sphere. So we're going to have that constant can just be pulled out of the integral here, q over v, and then I'm going to integrate r over, like this, r vector over r cubed dv prime. Okay, so let's explicitly figure out what r is. Okay, so if we've chosen our test charge to be at 0, 0, z for simplicity, then we know that our source charge is going to be located in Cartesian coordinates at r prime sine theta prime cosine v prime x hat plus r prime sine theta prime sine v prime y hat plus r prime cosine theta prime z hat. Okay, and this is just the polar coordinate expansion of, you know, like a point on this sphere that we're integrating over. So here's r prime, and we've taken Cartesian basis vectors, but their components are in polar coordinates. Okay, and so this should be familiar if you've seen, you know, polar coordinates being used before. And let me know in the comments if you want me to do a video kind of explaining more in detail how to derive these polar coordinate transformations. Okay, so we know this is our r and our r prime, and so our cursive r vector, which is the distance, again, the distance from the source charge to the test charge, is equal to r minus r prime by definition. And so this is equal to, you know, I'll just call it r prime x negative x hat minus r y hat. And then we're going to have a z minus r z prime z hat. Okay. And this is just, you know, this is just component notation for the vector r prime. Okay. Because I don't want to write it all out again. So plugging this in to our equation, we have an integral. Okay, we have 1 over 4 pi epsilon naught q over v. Now this integral is over the sphere, so I'm integrating the azimuthal angle from 0 to 2 pi, the polar angle from 0 to pi, and the radius from 0 to r. And then we're just going to plug in what we have. So we have negative r prime sine theta prime cosine phi prime. Oh, and it's going to be a lot. Let me grab some more space here. Yeah, so we're going to have negative r prime sine theta prime cosine theta prime x hat minus r prime sine theta prime sine phi prime y hat plus now z minus r prime cosine of theta prime z hat. And now this is our really gross expansion again of just this vector r here. Okay. Now the dv prime will come out as a r prime squared sine theta prime dr prime d theta prime d phi prime, with barely enough room to squeeze everything in. And then, so that's our dv prime. And then finally, we're dividing by the magnitude of r cubed. Now the magnitude of r is just the sum of the squares of its components, and then we take the square root. So magnitude of r is equal to rx squared plus ry squared plus rz squared square root. And really what this bottom piece is the magnitude of r cubed. And so r is just the vector I've written on the numerator here. If we take its magnitude, we notice that we're going to get an r prime squared sine squared theta prime, okay, where these two terms, the cosine and the sine of phi squared, will add to get 1. And then we're going to add with the square of this term, which is, I'll just write it out, z minus r prime cosine phi prime squared. And now we're going to have this term. This is actually the magnitude squared, so we're going to raise it to the 3/2 power. And that's pretty much it. Now I can rewrite this bottom term in a bit simpler form, because I recognize that when I actually FOIL this out here, this z minus r prime cosine theta prime squared, I'm going to have a nice cancellation that I can combine the r prime squared cosine squared theta prime with r prime squared sine squared theta prime, leaving me with a final form here of r prime, r prime squared plus z squared minus 2rz cosine theta prime. And hopefully I'm correct about that. Let me know if I'm not in the comments, but I'm almost positive that's the correct expansion. R prime here. Now, one thing I'll quickly notice is that this integral we're integrating, there's a nice symmetry about the, since we're considering the point z to be the test charge, it's totally symmetric about the azimuthal angle, i.e. as I rotate in this direction, kind of rotating the xy plane almost, and keeping the z-axis fixed, there's a symmetry that goes on in the direction of the electric field. And in particular, we should have everything canceling out except for the z component, right? We shouldn't have that, this half of the sphere contributes more than the opposite half, and so somehow the electric field is pointed away from the z-axis. That's not going to happen because the sphere is uniformly charged. And so we should expect this integral should vanish except for in the z hat term. And in fact it does, because if we look at the x hat and y hat terms, we have a cosine of phi prime and a sine of phi prime just sitting there. There's no other phi dependence anywhere, okay? And notice how we're integrating. This integral of the azimuthal angle phi goes from 0 to 2 pi. And so since these terms are completely independent of there's no other phi dependence anywhere, these cosine and sine terms are going to cause the integrals to go to 0, because the integral of sine phi from 0 to 2 pi is equal to 0, and is also equal to 0, integral from 0 to 2 pi of cosine phi, obviously d phi. So with this in mind, we can go ahead and cancel out the x hat and y hat parts of the integrand, and we know that they're both going to go to 0. And so finally, we're left with the beautiful 1 over 4 pi epsilon naught q over v integral from 0 to 2 pi. And when I say beautiful, I mean I'm like semi-sarcastic, but not even really sarcastic, because this really is beautiful stuff. So z minus r prime cosine theta prime z, and then I'll leave the z hat. Maybe let's put the z hat out in front. And now r prime squared sine theta prime d r prime d theta prime d theta prime divided by prime squared plus z squared plus 3 half. Okay, and now we have an integral. We have something, right? And this is our electric field, E of z hat. And now, due to radial symmetry, any z dependence here, I can just write that E of z hat, say I get this as a function of z, okay? Then basically I can rotate the sphere such that the z-axis is really just any point out in space, and I've just centered the vertical axis to be at that point, so I know that E at any point r is just a function of the radius, which is f of r, where I've just plugged in, instead of z here, I just plug in the radius instead. Okay, so yeah, this is pretty much how it's done, and the crucial calculation will come in evaluating this integral, unless you want to open up your calculus textbook and look, scroll through an integral table. You might want to use some sort of integral calculator to solve this. However, there's a better way. There's a better way to do this whole problem, and I'll put in the comments that if you want to, you can skip past everything I've done, past all the grossness of this brute force calculation, and now we're going to use some martial arts. Okay, now we're going to use maybe some weaponry beyond just our brute bare hands. Okay, and that is going to be Gauss's law. Okay, so let's start this problem again from a different footing and recognize that if you give me something like a sphere, okay, of uniform charge, then to find the electric field, I should immediately think, well, there's something useful I can use. It's called Gauss's law. And Gauss's law is built to exploit symmetry like this. So let's recall Gauss's law, which tells us that if I take a closed Gaussian surface, so say I take any surface, it doesn't have to be a surface that's charged, it's an imaginary surface inside of my three-dimensional space. So let's say I take, if I really wanted to, I could take an imaginary box around this sphere. Now that would be a terrible choice, but let's say I went ahead and did that. Then the integral, the surface integral over this box, or any closed surface, the crucial point is that the surface is closed, okay, of E dot dA, okay, I'll explain what that means later, is equal to the net charge enclosed divided by epsilon naught. So this is Gauss's law, okay? I really hope I got that right. So please go online, look this formula up, make sure I did it correctly, and also make sure that you understand where this formula comes from, because it's probably one of the most useful things in introductory electromagnetics. Now, we have a sphere here. We don't want to integrate over a cube because we need to exploit the symmetry in E dot dA. Okay, so the reason why Gauss's law is so useful is because we can look at this integrand here, E dot dA, and exploit some of its symmetries. So dA is the normal vector to the surface with magnitude dA, where dA is the familiar differential area, okay? And so if I take, for example, the normal vector to a sphere, well, that's always going to be pointed radially outward. And so I want to integrate over a surface where my electric field has some sort of symmetry with the normal vector to my Gaussian surface. And if that happens, then this dot product, as you'll see in a minute, becomes extremely easy to evaluate and simplifies the problem tremendously. So in the case of a sphere, clearly we should not be integrating over a Gaussian cube. That makes absolutely no sense. We would want to be integrating over a Gaussian sphere, okay? So I'm going to take a sphere that's concentric with my charge distribution and larger in radius, okay? and this is, my notation is terrible. Let's call this Gaussian sphere G. Okay, so I'm actually going to integrate over G, not the charged sphere. And in this case, E dot dA, well, I know the electric field is also pointing radially outward, just due to symmetry that we talked about earlier. And so since the electric field is pointing radially outward, it is always parallel to the normal vector to the sphere. Okay, so any vector that's normal to this Gaussian sphere G is going to be directly parallel to the electric field. And so because of that, E dot dA, remember the dot product is just E dA times the cosine of the angle between them. If they're parallel, that just becomes E dA, okay? Where E is the magnitude of the electric field. And as we talked about earlier, dA is the magnitude of this dA vector here. Okay, and this is just a constant. This E is just a constant because it's radially symmetric. Everywhere it's going to have the same magnitude. It's the only thing that's going to change is the direction, okay? And so I can just pull the E out. It's just a constant. It's the magnitude of the electric field at a fixed radius. And now I have the surface integral of dA. And this surface integral of dA, well, I'm just summing all of the differential area elements over the whole surface. Well, that's just the area of the whole surface. So that's E times the surface area of the Gaussian sphere. Let's call the Gaussian sphere to have radius, G of radius R. Then this surface area is going to be E times 4 pi R squared. And by Gauss's law, that's equal to the Q, the net charge enclosed, which is just the charge of the sphere, divided by epsilon naught. Wow, this is so much simpler. I get E is equal to 1 over 4 pi epsilon naught Q over R squared. Okay? And notice this is the magnitude of E, and so I'm going to get that the actual vector E, again exploiting what I know about the radial symmetry, is just going to be E R hat. So again, I know its magnitude, that's what I've solved for, and its direction is always going to be radially symmetric, so it's just pointed in the R hat direction. 1 over 4 pi epsilon naught Q is the charge of the sphere, over R squared times R hat. And we have something very interesting that shows up. First of all, we've solved explicitly for the electric field in such a simpler form and so quickly compared to trying to use brute force and getting this monster of an integral. But make no mistake, this integral will evaluate to the exact same thing as what I've just calculated using Gauss's law. These two are identical and they're both correct solutions. It's just Gauss's law is insanely more powerful in this specific kind of scenario that I've concocted here. And the other thing I want to point out is that the electric field of this uniformly charged solid sphere is the same as if it was just a point charge. Okay? So turns out that the symmetry of a point charge, it's radially symmetric. The symmetry of a solid sphere, radially symmetric. And as long as they have the same charge, Gauss's law says the electric field they generate is the same. Obviously, we're considering points outside of the sphere, but this is pretty remarkable that, it doesn't matter the size. I can have an infinitesimally small point charge or as big of a volume charge as I want, as long as I have spherical symmetry and radial symmetry. The electric fields they generate will be the same, okay? Assuming they have the same charge. Now, this is a remarkable conclusion. It's not trivial at all. Gauss's law literally plows through this problem and utterly destroys this problem. And I challenge you to go and do the integral, do the brute force method yourself. Maybe even use a different method than what I've shown here, using maybe the integral for the electric potential, which is also a possibility. Let me just remind you, you could have also used V is equal to 1 over 4 pi epsilon naught, the integral of dq prime over S over just magnitude of R, which is much simpler than even the calculation that I was doing, but it's still going to be a gross integral. So why don't you try solving for this using brute force and verifying that integral is indeed equal to this result that we've gotten here using Gauss's law. One last thing that I want to comment on is that Gauss's law is extremely powerful in situations where you can exploit symmetry, okay? Notice how gross these integrals are in electrodynamics. That's kind of a thematic trend is really gross integrals in polar coordinates. At least that's what Griffiths loves to kind of bring about. Gauss's law destroys problems where E dot dA has some sort of inherent symmetry. That means dA is of course in the direction of the normal vector to the surface that I create. And so if I know the electric field has some sort of inherent symmetry, let's say I know that it's cylindrically symmetric, maybe it's generated by a cylindrical charge distribution, or maybe it has, maybe it has some sort of horizontal or vertical symmetry. Whatever the case may be, if I can find that symmetry and then create a Gaussian surface that exploits that symmetry, exploiting it by making this dot product here, by making this dot product very easy to compute. So so easy that it just gets destroyed right off the screen. Yeah, if I can make this dot product easy to compute, then Gauss's law is extremely useful. And the way you do that is by exploiting symmetry and things that you know are the case about the electric field. All right, that's all I got for y'all today. Have a nice rest of your night.